Okay, so in this video we're going to talk about using law of sines to solve for all the dimensions of a triangle, right? So we know law of sines is basically telling us that for all triangles, the ratio of the sine of an angle to the opposite side is equal for all three angles and their corresponding opposite sides. And what we can say is, if we're given three dimensions that include one ratio, right, one angle and its corresponding opposite side, then we can use that ratio to solve for all of the dimensions that we're missing in a triangle. And we can do this in three scenarios: when we have angle, angle, side, angle, or side, side, angle. Now right here, angle, angle, side, and angle, side, angle are both congruence relationships for triangles. So basically what that means is they're going to define one triangle, right? And what that means that we're going to be always solving for the dimensions of one triangle. Side, side, angle is not a congruence relationship, and this means that we're not always going to get just one triangle. It could be that we have one triangle with side, side, angle. It could be that the dimensions will give us two different triangles, or it could be that the dimensions give us no triangles. And we're going to investigate that in a little bit. So what we want to do right now is just go ahead and solve for a triangle, solve for all the dimensions that we're missing in our triangle, given angle, angle, side, and angle, side, angle. So right here, let's start with angle, angle, side. So right here, we're given angle A is 36 degrees, angle B is 48 degrees, and side A as length 8 for some triangle. So right here, let's draw that triangle. We draw that triangle, looks like this. Right here we've got our angle A, right? We've got our angle B, and we've got our side A opposite our angle A. That means that the dimensions we're missing are side B, angle C, and side little c. So right here what we're going to do is set up the ratio that we have, which is the ratio for A, right? Angle A to side A. So we've got sine of 36 degrees, that's angle A, to our length of 8, which is the side opposite A. And right here we're going to set that equal to the ratio involving the other dimension that we're given, right? So the other dimension we're given is angle B, so we're going to say sine of angle B, 48 degrees, over, and then side B, which is one of the dimensions we're missing. Now right here what we've got is an equation involving the variable side little b. And right here what we can do to solve for b is basically just multiply b on both sides. And now right here what we can also do is after we multiply by b on both sides, we can multiply by the reciprocal of sine of 36 over 8. And when we do that, what we're given is b is equal to, right here, 8 sine of 48 degrees over sine of 36 degrees. And right here that gives us side B as 10.11. So we've got side B as a length 10.11 of some unit. We're not specifying the unit here. Now right here we don't have angle C or side C, but we do know that there are 180 degrees in a triangle, right? So we can say that angle C must be 180 degrees minus the sum of the other two angles, 36 degrees and 48 degrees. And that's going to give us our angle C as 96 degrees. And now since we've got angle C, we can use our original ratio in the same way we did with angle B to solve for side little c. So right here we can say now that sine of 36 degrees over our side of 8 equals sine of 96 degrees over side little c. And then right here we multiply c on both sides and then multiply by the reciprocal of sine of 36 over 8. And that gives us c as equal to 8 sine of 96 degrees over sine of 36 degrees, and that gives us our side little c as 13.53. And those are all the dimensions. So right here, What we want to try to do is get one ratio and use that ratio through the whole problem. Now, we want to use this ratio through the whole problem because it's got the most accurate numbers in it. So right here, it's going to give us the most accurate outputs for all of the dimensions we're solving for. So right here, with angle side angle, if we look, we can say that the dimensions we're given aren't actually giving us a ratio. But we do have two of our three angles, right? So we can solve for our angle C by saying we know that angle C is going to basically be 180 degrees minus the sum of the other two angles, 25 degrees plus 41 degrees. Now right here, that'll give us angle C, which we'll be able to use in a ratio with side C to solve for the other two sides that we're missing, side A and side B. So why don't you guys go ahead and give that a shot, and we'll come back and look at this in a second. Go ahead and pause the video and give this a shot. Okay, so we can solve for our angle C right off the bat by saying that we know that angle C has got to be equal to 180 degrees minus the sum of the other two angles. That gives us angle C as 116 degrees. Now we've got our angle C and our side C, and we can use those in a ratio to solve for side A and side B, the other two dimensions we're missing. Right here, we've got sine of 116 degrees over 8 equals sine of 25 degrees over A, multiplied by A on both sides, then multiplied by the reciprocal of sine of 116 degrees over 8, and that gives us A as 8 times sine of 25 over sine of 116, which gives us our side 8 as being of length 3.76. Then right here we can do the same thing with B. We'll multiply B on both sides, then multiply by, again, the reciprocal of sine of 116 over 8, and that gives us B as sine of 41 degrees over sine of 116 degrees over 8, and right here that gives us side B as being of length 5.84. Okay, so moving on, let's talk about the scenario of side-side angle. So initially, the first scenario we're going to talk about is the scenario where the side opposite the angle we're given is longer than the side adjacent to the angle we're given. So right here, in the scenario where we have side-side angle, we're going to have two consecutive sides and then the next angle. So right here, we have side A, side B, and angle A. Let's set this up. So right here, let's say that this guy right here is A. That means that we're going to have now two consecutive sides from that angle. So right here, the side next to angle A is going to be side B, and that's of length 5. And then the side opposite A is always going to be the corresponding lowercase letter, so that's going to be little a, and that's going to be of length 8. Now, the thing that we want to take note of is that there's only one way for this opposite side A to fit with its end to B within the angle A. So right here, with this scenario, we're only going to get one triangle, right? And we can just set up our ratio and solve for that one triangle. So right here, we're going to say that sine of 43 degrees over our side of 8 is going to be equal to the corresponding ratio with the other dimension that we're given. So right here, we're going to be able to say sine of B. We don't have B, but we do have the side B of 5. And now right here, what we can do is solve for sine of B by multiplying 5 on both sides. And when we multiply 5 on both sides, we get sine of B equals 5, that's 5, sine of 43 degrees over 8. And right here, this gives us sine of B, 0.4262. Now at this point, we can apply inverse sine to both sides and solve for our angle B. So right here, on this side, the inverse signs will cancel. And on this side, the inverse sine will give us the angle that gives us the ratio of 0.4262. So right here, that gives us angle B as being 25.23 degrees. Now that we've got two angles, we can solve for the third angle because we know the sum of the angles of a triangle, 180 degrees. So that means that angle C has got to be 180 degrees minus the sum of the other two angles. That's our 43 degrees, and then plus our 25.23 degrees. And that gives us our angle C as being 111.77 degrees. Now right here, we've got two of the three dimensions we're missing, the two angles. And right here what we can do is go ahead and solve for that last dimension, our side C, by using our original ratio, sine of 43 degrees over 8. And we'll set that equal to sine of 111 degrees, 111.77 degrees over our side C. Solve for C in the exact same way, multiply C on both sides, and then multiply by the reciprocal of sine of 43 over 8. So C is going to be 8 sine of 111.77 degrees over our sine of 43 degrees, and that's going to give us side little c as being of length 10.89. So that's a lot of me doing the work. But right here what we're going to do is move on to the more complicated scenario. So if the side opposite the angle we're given is larger than the adjacent side, we've got one triangle and not that much to worry about. If the angle is acute and the adjacent side is longer than the opposite, then we have the ambiguous case. And let's explore this. Right here, we've got our angle A is 30 degrees. We've got our side B is 7 and our side A is 5. So let's set this up. We can say, here's our angle A. That means the side adjacent has got to be B, which has to be of length 7. And then right here, our side A is going to be opposite our angle A, and that's going to be of length 5. Now right here again, what we want to remind ourselves is that angle C, side C, and angle B can be of any measure, right? So right here, there are two ways that this smaller side A can fit within this angle A so that its end is touching B. It can fit right here and give us what we'll call B1, the acute angle B, or we can pick it up and put it down over here, and we'll get that same length of 5, fitting within our angle A. Let's try to draw this accurately. And giving us a second triangle with an obtuse angle B that we'll call angle B2. So right here, let's take these two triangles and separate them. This is what we're going to call our triangle 1 with our acute angle B. So right here, we'll call this B1. We've got angle A over here, side A. We've got side B. Angle A, side A, and side B are all the same dimensions, right, in both triangles. But right here, we're going to see angle B1, C1, and side C1 as being different dimensions from B, angle B, angle C, and side C in our second triangle. So again, right here, A, B, and A, angle A, side B, and side little a, are the same dimensions. But right here in our second triangle, we have an obtuse angle B, we'll call B2. We've got a smaller angle C, we'll call C2, and a smaller side C, we'll call little c2. Right? Now right here, if we look at these two triangles, right, when we set up our ratio, basically what we're going to see is sine of our angle 30 degrees over our side of length 5 equal to sine of angle B over our side of 7. Now right here, what we're going to do is, of course, multiply by 7 on both sides and then take inverse sine of both sides to get our angle B. Now, which angle B is it going to be? Is it going to be B1 or B2? Well, right here, if we remember how inverse sine evaluates ratios and gives angles, if we're talking about inverse sine, it's going to give an angle measure on the right side of the unit circle. Now, right here, that means that for positive angle measures, it's going to give out angles between 0 degrees and 90 degrees, right, in that first quadrant, right, which means that the angle B that we're going to get from our calculator is going to be that angle B1, right? So the calculator will give you angle B1. But the thing we want to notice here is we've actually got a triangle, an isosceles triangle, within our two triangles created by that side A equals 5 being repeated. And basically what we're seeing from this isosceles triangle is that right here, this angle B1 is congruent with this angle on the other side of the isosceles triangle. And that means that angle B2 and angle B1 are supplementary angles, which means that they add up to 180 degrees. So once we get our angle B1, we'll be able to solve for our angle B2. So what I want you guys to do right now is to go through and solve the first triangle here. First solve for our angle B1 and then go through and solve for our first triangle. And then we'll come back and we'll set ourselves up for the second triangle, and then we'll solve that second triangle. So give the video a pause and solve triangle 1. Okay, so solving for B1, we can go ahead and solve for sine of B1. That'll give us sine of B1 equals 0.7. And then right here, applying inverse sine to both sides, we get angle B1 as 44.42 degrees. Then right here we can say angle C1 is going to be 180 minus the sum of the other two angles, which gives us angle C1 as 105.58 degrees. Then right here we can go over and use our original ratio of sine of 30 degrees over 5 with sine of angle C over side little c1 to solve for side of little c1, multiply little c1 on both sides, and then multiply by the reciprocal of sine of 30 degrees over 5, and that gives us 5 sine of 105.58 degrees over sine of 30 degrees, which gives us c1 as 9.63. Okay, so right here, we've solved our first triangle, right? That's the first possible triangle we would get from these dimensions with side-side angle. Now right here, moving up to our second triangle, we know that we can solve for our angle B2 by taking 180 degrees and subtracting away our B1, which we know is 44.42 degrees. So right here, 180 degrees minus 44.42 degrees gives us our angle B2 as being 135.58 degrees. And there's our angle B2. Now right here, we know that the sum of angles in a triangle is going to be 180 degrees again. So right here, we can say that angle C2 then has to be that 180 degrees minus the sum of the other two angles. Remember that this angle A is the same as this angle A, which is 30 degrees. So right here we're saying 180 minus 30 degrees. And then right here, plus 135.58 degrees. And that gives us our angle C2 as being 14.42 degrees. And now right here, with that angle C2, we can go ahead and solve for that last side C2. So right here, sine of 30 degrees over our side of 5 is equal to sine of 14.42 degrees over C2. C2 is going to equal 5 times sine of 14.42 degrees over sine of 30 degrees, which gives us side C2 as 2.49. And those are 3 lengths for our second triangle. Okay, so we'll definitely try one of these on Wednesday, and we'll talk about the scenarios where we can spot them. Again, this is basically when we've got side-side angle, and the side opposite our given angle is shorter than the adjacent side. We're going to have the possibility for 2 triangles. What we want to say real quick before we move on right here is that there's also the possibility for no triangles or 1 triangle. If the opposite side A is just long enough to come down and reach that other side, we're going to get 1 triangle, and it's going to be a right triangle. If that opposite side A is too short, then we're going to get no triangle. So here we'd have, there's our angle A, there's our side B, and our really short side A, and right here in this case we would say no triangles. And here's our 1 triangle. Now right here in this case, what you're going to get is basically that angle B will be 90 degrees, a right triangle, right? And then of course, if you were trying to solve for an angle B2, you would get 180 degrees minus 90 degrees, which would give you 90 degrees again. That's that 1 angle. Right here, what you're going to end up with in the calculator is an error. So if we had this scenario, immediately you would get an error because no triangles would be possible. Okay, so we're going to stop this video now, and we are going to go ahead and talk about law of cosines on the next